Welcome to example number 15, which we label as the primitive yo-yo, or you can simply call it the falling disc lab. So the figure to the right shows a primitive yo-yo, which is in the form of a solid disc with the mass m and radius r, that is being released from rest with a supporting hand, and as the string unwinds out of this disc without slipping. So part A is asking to draw a free body diagram showing all the forces acting on the cylindrical yo-yo. Part B is asking for the speed of the center mass when it gets down to the bottom. C is asking for what is the acceleration of the yo-yo. D is find the expression for the tension. And E is if you were to change this problem from a solid cylinder to a hoop, how would all of your answers change? Okay, so I'm actually going to skip to part B first. And you'll see why in a bit. Uh, because in part B, we're asked to find the velocity of the center of mass. And you can see that there's an angular velocity involved in here. And we don't need to go through all of the bit of finding the acceleration that you get in, say, part, say, C or D to find out the speed. You can actually get the speed of the center mass by just using a conservation of energy approach. That would be the easiest way of doing it. So let's go ahead and do that. So the energy initially is equal to the energy finally. So if you look at the disk at the beginning, it has potential energy. And we're going to say down here, at this point, that height is going to be 0 relative to the center of it. So we have gravitational potential energy initially. And then as the yo-yo falls, it's going to be converting it into a rotational kinetic energy, which is 1/2 I omega squared. Plus, it also has a translational kinetic energy, which is 1/2 mv center mass squared, because this is moving that center mass. So we want to find out an expression for the velocity of the center mass in terms of g and h, but we've got this I and omega to kind of get rid of. Now, remember that we said that this is a solid disk. So we need to look up the rotational inertia for a disk. And if you go look back at the notes, you will find the rotational inertia for a solid disk is 1/2 mr squared. It also could be listed as the rotational inertia of a cylinder. It's the same thing. So we're going to replace I with 1/2 mr squared. We also know that the angular velocity is equal to the velocity of the center mass divided by the radius of the cylinder or disk. So let's replace these two into here and here. We're going to mgh equals 1/2 times 1/2 mr squared, and then the angular velocity replacing with the velocity of the center mass divided by r quantity squared plus 1/2 m the velocity mass center mass squared. And if you simplify this, you will see that you'll have a 1/4 here m, and then the r squared here will cancel with the r squared from over here, and so you'll really get 1/2 mv or 1/4 mv squared plus a 1/2 mv center mass squared. By the way, if you notice, there's an m in every term. So not only can we cancel out the radius, again, the masses cancel out, so it's independent of the mass. So we get gh equals 1/4 plus 1/2, which is really 3/4 v center mass squared. So the velocity of the center mass is really equal to the root of 4/3 gh. So that's the answer for part B. Okay, now let's move on to part A and then C and D kind of together. So we're now trying to come up with an expression for the acceleration of the yo-yo. So we're going to first draw a free body diagram for this. So I've redrawn the hoop over here. You can see that there's a string pulling upwards on it over here. So that means that there's a tension going straight up. And then also from the center, which we assume all of the mass of this disk is located at the center of mass, so we're going to draw the center of mass. Which of these two forces is bigger? Well, remember, it's accelerating downwards. So if it's accelerating downwards, then the gravitational force has to be bigger. That's the bigger force compared to the tension. Okay, so our free body diagram is done. So now we're going to proceed on to part C, where we need to determine, it's really kind of C and I guess D actually. We're going to determine an expression for the acceleration and the tension in this string. So I'm hoping you're thinking, well, if we're going to try to find tension and acceleration, we're going to have to use rotational dynamics and some translational kinematics as well. So if you just look at this in terms of F equals ma, you have sum of F along the y-axis is creating, let's assume our y-axis is positive going downwards, is equal to m times a. And that's an acceleration of the center mass right here. The net force that's caused by this is due to these two forces. With gravitational force is bigger than the tension force, it's going in the positive y direction, as I define y being positive downwards, and the tension is going upwards. So we really have the force of gravity minus the force of tension that gives you this net force of ma. You can replace the force of gravity with m times g, that's the mass of this disk, minus the tension equals the mass of the disk times the acceleration of the center mass. So we got to this point. This is a nice expression here. What we want to do is get A by itself, but we need to get rid of tension. So we need to get some other expression that involves tension. We've applied Newton's second law in the translational version, but hopefully you realize that it's also angularly accelerating due to an unbalanced torque by this force mainly. This force is not really producing any torque about the center. So we're now going to apply the sum of torques about a pivot point P, and that point P is going to be about the center of its axis of rotation right here, center mass. And that's going to be equal to I of the disk multiplied by the angular acceleration alpha. Remember, the force of gravity is not going to produce any torque because it's the force being multiplied by the distance, but the distance r in this case is 0. So there's no torque being produced by the weight of the disk. It's only really a torque being produced by the tension. So our torque from the tension will be Ft multiplied by this distance r, and then multiplied by the sine of the angle theta. And that angle theta would be actually 90, which will cancel out to be 1. And then I is I for disk, which we wrote earlier here as 1/2 mr squared. So we're going to rewrite that as 1/2 mr squared. That's for I. And then also the angular acceleration. Remember, the linear acceleration is the radius multiplied by the angular acceleration. So the angular acceleration is the linear acceleration divided by r. That's the acceleration along the center mass. So the acceleration of the center mass divided by r, but we're going to be replacing the angular acceleration. And then you can see some cancellations occur. One of these r's cancels out with one of those r's, and this r then cancels out completely with the other r. And so you don't get any dependency of the radius at all. So we see that the tension that is acting on this disk is really equal to 1/2 times the mass times the acceleration of the center mass. So we've got two equations, equation number 1 and equation number 2, and we're trying to solve for the acceleration, hopefully in terms of m's and g's, and that's about it. So let's sub 1, or actually equation 2, into equation 1. We're going to get rid of this ft and replace it with that now. So we have m times g minus 1/2 mass times acceleration of the center mass equals mass times acceleration of the center mass. When you bring that over to the other side, you're going to get 1 plus 1/2, which is 3/2 times mass times acceleration of the center mass, and then mg. And oh, look at that, m's on both sides. The m's cancel out. The mass is irrelevant. So the acceleration of our yo-yo disk, or permitted yo-yo, is going to be 2/3 of g. And that's the answer for part C. Now we need to find the tension. Now the tension we know is 1/2 of ma, but let's replace this acceleration into here. So now we have Ft equals 1/2 m times 2/3 of g. So then the tension becomes equal to, these 2's will cancel out, and it'll be equal to 1/3 of the weight of the yo-yo. So you can see it interesting as you reflect upon this, the masses cancel out, making the mass irrelevant. Doesn't depend on the mass of the yo-yo at all. Furthermore, the radius of the yo-yo canceled out as well. That didn't make any effect on the acceleration or the tension. And notice that the acceleration was 2/3 of g. So it's basically less than g. So when you let go of the yo-yo, you're going to have it falling downwards, but it's not going to be accelerating as quickly as if it were just simply dropped. And the tension is not going to be, is going to be 1/3 of the weight of the yo-yo. Now, what would happen if you changed this whole problem and just did a hoop instead? How would that change? Without redoing the entire solution, I'm just going to actually kind of just substitute in here to show you how the answers would change. The I of the disk is 1/2 mr squared, but we want to know what I for hoop is. The I for the hoop is mr squared. So then we're over in here, we're going to replace that with mr squared, which is then going to change our answer down here and here, and then inside here. So instead of getting a quarter there, you're now going to have a half, and then 2 halves added up to a whole, and you're just going to get GH. So earlier it was 2/3 of 4/3 of GH, and now it's just GH, so it's not going to have as quick of a velocity. The free body diagram is going to be basically the same. This will change over here. You're not going to have a 1/2 mr squared here. You're going to just have mr squared, and then that's going to change all the answers down here. So that changes over here from being a half to a whole. Then you get 2. And then solving for the acceleration, you're only going to get 1/2 of g, where earlier you had 2/3 of g, so it's now accelerating at less of a value. And then consequently, your tension is going to be just 1/2 of mg if you substitute through in here. So with a greater rotational inertia, your velocity at the bottom is smaller, right? And your acceleration is smaller, and your tension is more than what you had earlier. So as we kind of summarize this, you can see that both the hoop or the disk, as they fall, they're losing gravitational potential energy and transforming it into rotational kinetic energy and translational kinetic energy. Now, the hoop has a larger rotational inertia I, and so it's essentially harder to rotate. It will take they both start off, say, with the same gravitational potential energy, yet for the hoop, it's going to be transferring more of this potential energy into the rotational kinetic energy because it has a larger value of I, and because it's going to be taking a larger share of this total energy, then it's going to leave less kinetic energy translationally. And that's why, in the end, the hoop is going slower, and hence it has a smaller acceleration. Hopefully that all makes sense conceptually. If you want to kind of see it to believe it, I'll post some videos of links showing you a falling disc and a falling hoop, and you can see just by looking at the video which one is accelerating larger and which one's reaching the bottom at a faster velocity. And that's it for this example.